multi-class activation functions. Notice that in our previous topic we discussed about the neural networks where we had only a single output, that is the output of a neuron was a single node. But what if we need to have more than one output from a single neuron? So there comes the idea of multi-class activation functions. So let's discuss about where the idea of multi-class activation functions come in. So let's say if we want to have more than one node as the output node, then what should we do? In that situation, the multi-class activation function comes in. So the main difference between a multi-class activation function and a normal activation function is that the normal activation function will always have a single output node, but in multi-class activation function there will be a different situation where the output will have more than a single node, and we have divided those multi-class situation into two different categories. Those are, the first one is mutually exclusive situation and the second one is non-exclusive situation or classes. And now let's discuss about the non-exclusive type of classes. And in non-exclusive classes, a data point can have multiple classes or categories assigned to it. Let's take an example of a mobile phone. It can have multiple tags like company name, vendor name, its type, its color, and many more. And another case of multi-class activation function is the mutually exclusive classes, where a data point can have only one classes or categories assigned to it. Let's take the same example that we took for non-exclusive type. There was the type of a phone, and in a mutually exclusive situation, a mobile phone can have only two categories. That is, either the phone can be a Android phone or it can be an iPhone. A mobile phone cannot be an Android and iPhone at the same time. So this is an example of mutually exclusive classes. And let's look at a broader concept. The biggest challenge in this multi-class activation function is to organize the output. How many output do we need? How many outputs should we have? So the easiest way to manage and organize this multi-class activation function is to have one output node per class. So previously we thought that the last node was the output node in the neural system or neural network, and the single output node could have an output of simple regression or continuous values that ranges from 0 to 1. And now let's convert this simple type of neuron into a multi-class neuron. There were 4 input layer, and the middle one was the hidden layer, and the output layer had only one single node. And while classifying this as the multi-class activation function or multi-class operation, we can see here we have multiple input and hidden layer, and the output has 3 different nodes. There are 3 different nodes, class 1, class 2 and class 3 respectively. And moving on, we'll need to organize the categories for the hidden layer. We cannot just have categories like cat, hen, dog and etc., mobile phone and other strings. The neural network does not understand string values, so we want to convert those string values into binary values, that is 0 or 1. For that we'll use one-hot encoding system in this situation. We can see here for mutually exclusive classes, the neuron does not understand English language. Like we have data point 1, 2, 3 and 4, and the colors are red, blue, green and blue. The neural network won't understand these string values like red, blue, green and blue. The neural network won't get it. So what we need to do is that we have to convert these string values into binary values. Those are zeros and 1, by using the one-hot encoding system. And we can see here mutually exclusive classes. We discussed before that in mutually exclusive classes, a data point can have only one category assigned to it. So we can see here the data point 1, 2, 3 and 4, and the colors are red, blue, green and blue. And by using this one-hot encoding method, we keep the same data point, and now we'll convert this data set into a matrix type data set. That is, we have color red, color blue and color green. We can see here data point 1 has a red color, so here we'll write 1 in the data point value 1 where the color is red. And we can see here we don't have any blue or green value in data point 1, so we'll need to write zeros, that is off. And we can see here in data point 2 we have blue, so in data point 2 we'll need to write 1 where we will have the color blue, that is we have color blue here. So in data point 2 we write 1 here, and we don't have any red color or green color here in our data set, so we'll write zeros respectively. So I hope you guys understand this classification with one hot encoding method. And now we'll move on, and now let's discuss the non-exclusive classes. And this one is quite different from the mutually exclusive classes, because in the mutually exclusive class we had only one category assigned to a data point, but in a non-exclusive class, as we said before in the beginning of our topic, that in non-exclusive classes a single data point can have more than one categories or classes assigned to it. We can see here we have data point 1, data point 2, data point 3, and much more between them, and the last one is data point n, say data n. We have a comma b as the value of data point 1, a as the value of data point 2, c and b as the value of data point 3, and b as the value of data point n. Now let's use the one hot encoding method to convert this string data into a binary form of data. We can see here, let's classify this data. We can see here data point 1, data point 2, data point 3, and data point n. This is same as we discussed before in our exclusive type classes. See here, it is almost same. The only difference is that we have multiple classes and categories assigned to a single data point. We can see here in data point 1 we have a value a, so we write here 1. We have a value b, so we write 1 in b also. But we can see here we don't have any c value in data point 1, so we'll have to write 0 in the data point 1. And in data point 2 we have value a, so we'll write 1 in the a section and zeros in b and c section. Why? Because we don't have any value of b and c in the data point 2 section. So furthermore we'll do the same process for coming data points. And the organization of our data is now completed. Now the greater challenge is that what activation function will we have to use for a efficient output. As we discussed before, we have two types of multi-class activation function. Those are, the first one is non-exclusive, and the first one is non-exclusive type, and the second one is mutually exclusive type. For non-exclusive type classes, we'll use sigmoid function, the same function that we discussed before in our previous video. We can see here this one is the y line, this one is the x line, and the value of output may range from 0 to 1, any value between them, any value between 0 and 1. That can be 0.1, 0.2, that can be 0 as well as 1. So for non-exclusive classes we'll have to use the sigmoid function. So moving on, we can see here we have applied a sigmoid function for our neural network. Here we can see we have the first node as class 1, second node as class 2, and further the last node as class n. And for the mutually exclusive classes we'll have to use the softmax function for a proper output. So we can see here the formula for softmax function is this, and we have I value that ranges from 1 to k, and k is the different classes we have. So what this softmax function does is that it calculates the probability distribution of event over k different events, and the output will range from 0 to 1. That means we can have the output as anything like 0, 0.1, 0.2, anything, any value that ranges from 0 to 1. And the one peculiar condition of this softmax function is that the summation of all the output values from respective classes is always 1. We can say that this softmax activation function outputs the probability of each class, and the target class will be chosen as per the highest probability of the output class. Let's take an example. If the output node has the highest value, that is any highest value in that respective neuron, then that output node will be taken as the target class. We can see here in mutually exclusive classes, when we use this softmax function, the output is derived as this: red, green, and blue. We can see here this value, these numeric value are the probabilities of the respective classes. We have probability 0.1 for red, 0.6 for green, 0.3 for blue, and we can see here the highest probability is 0.6, that is of green. So we'll choose the target class as green. Why? Because the probability of green class has the highest value. As we said before, the summation of all the output from respective nodes in a single neural network will give the value 1, while we use softmax function in mutually exclusive cases. We can see here when we add 0.1, 0.6 and 0.3, we'll get the output as 1. So let's review what we discussed in our previous videos and this video. The first we discussed was about expanding the perceptron model to a fully fledged neural network. We discussed about weight and biases, activation functions, and many more. And in further upcoming videos we'll be discussing about cost functions. You guys might have noticed that we discussed about weight functions, we discussed about weights, biases, activation functions, but still we don't know how we apply weight, how we apply bias to any neural network. So in further upcoming videos we'll discuss about how we apply weights and biases in our neural network. For applying that, we'll need to learn about cost functions and backpropagation method first, and in another video we'll be discussing about cost functions, gradient descent, and backpropagation. And thank you for watching the video, and don't forget to like and subscribe to the channel.